Problem set number 3, question number 5. So this one is all about the Poisson distribution. For the purposes of this question, we could just focus on the homicide row. The other data came with the data set, and I had explored some potentially fun things to do with those data, but in the end managed to do everything I needed to with the homicide row, so hopefully you also just stuck to that. Part A was dealing with the headline and whether or not there was a threefold change between the prior year, implied to be 2016, and 2017. Well, 2017 was 8, 2016 was 4. 8 divided by 4 is only a twofold change, not a threefold change. So nope, headline is incorrect. Part B, we're asked to identify or to calculate the expected number of homicides in a given year. So an expected number is an empirical probability, and that is, for us, the average. So on average, how many homicides happened per year? So we can highlight that and just look down here and see what's 1.55, or we could use the average function for those, or we could sum up the total number of homicides divided by the number of years. So this is just a simple mean, a simple average, the way we always would, no weighted averages involved. All of those give us the same answer of about 1.6 homicides per year. All else being equal, that is what we would expect in any given year. Now, this has a decimal, is 1.6, so any given year we don't expect a 0.6 of a homicide to happen. We only have whole numbers of homicides, either happened or didn't. So that means leads us into doing probability calculations for counts of data given expected rates. And in this particular case, we don't really have an upper bound. There's not, unlike the fire data, for instance, where we're looking at 16 years and wanting to know how many years of those 16 had fires, we don't have an upper bound for homicides, at least not practically speaking. There could be 0, 1, 2, up to who knows how many. Again, no fixed number of trials. So when we're asking for a probability for a count, for a specific number of things happening, when we don't have an upper bound, that is our cue to use the Poisson distribution and the Poisson function. So part C and D, and in the end, part E, are all using that. So for part C, we're asked for the probability of no homicides in a given year. So there's our 0 homicide. We've already identified that we want to use the Poisson for this because we have no upper bound. We can't use the binomial. So in Excel, because we want a probability, we're using the .dist kind of function, and it's Poisson.dist. And we need to give it the expected number that we're interested in. So we're interested in 0 homicides. In this case, the average number of homicides, sometimes known as the rate. So for us, that is 1.56 homicides per year. And we do not want a cumulative probability. We want the specific probability linked to 0 homicides. So false in this case. And it tells us that the probability based on this particular rate using the Poisson distribution is about 21% for no homicides. For part D, we do it the exact same way, exact same formula, except we're asking for 1 homicide instead of 0 homicides. And we get about 33% for 1 homicide. We then jump to part E, which asks in kind of a roundabout way with this RCMP question. So if we go back to the original data, we see prior to 2017, we have relatively few homicides, so 4 is our maximum value. And then 2017, we get 8 homicides. So the question was supposed to get you thinking. You've noticed this trend now, or the last part of my questions are the thinking questions. Given that all of these are low, and suddenly we doubled the number of homicides in 2017, should that be a flag to the RCMP that something is different. I did the underlying homicide rate, that 1.56. Did that change in 2017? Now, quite a few people correctly identified that Whitehorse has 40,000 people in it, and so if we're only talking 8 homicides, the overall rate, the overall empirical probability of being murdered in Whitehorse is very small. So it doesn't matter if it's 4 or 8, the underlying probability is still very small. And that is true. And the RCMP would probably, in reality, still say, yes, the probability is small, so people don't worry about it. Uh, Ultimately, that's not, even though I gave you credit for that, that's not what I wanted you to get out of the question. I wanted you to evaluate whether or not, given this 1.56, it was likely to get 8 homicides. If it is likely, however you defined that, then the RCMP can go ahead and say, nope, we think everything is the same and it's just a random fluke that we happen to get 8 homicides this year. On the other hand, if based on this particular rate and the Poisson distribution, if it was unlikely for us to see 8 homicides, then it suggests that, at least in 2017, this rate is not correct. That something changed between the before and this particular rate and 2017 that led to a higher homicide rate. So maybe there was a decrease in the economy and more homelessness. And I don't know what. The question doesn't ask you to speculate on why the change might have been there. It does, or at least the point was, for you to speculate on whether or not there was a change based on the probability. So in order to solve that, we keep doing what we were doing earlier. We ask, well, what is the probability of getting 8 homicides using this before, this prior to 2017 rate? And we see it is a very small probability. So the chances of getting 8 homicides under this rate is really small. Apparently I can't spell really. So even though people were correct and the overall chances of being murdered are small, there is a good chance that the underlying rate, this 1.56, did change in 2017. So that was that.